started on three-phase induction motor, and I was talking briefly about the three-phase machines in general, and we started off with the structure of stator and rotor. So we said first that the stator, which is the outer member, will have basically the three-phase winding housed inside that. So we are going to have the stator somewhat like this, with slots in the inner periphery like this. So this is how the slots are going to be. So I'm just showing the slots somewhat like this, and we are going to have the windings in the slot like this. So we are going to have the windings inside the slot like this, which will be actually a three-phase winding. So I will have R, Y, B specifically, or A, B, C phases wound independently, but the axis will be in such a way that if A phase axis is somewhere here, B phase axis will be somewhere here, and C phase axis will be somewhere here. All the three of them will be 120 degrees shifted from each other. That is how they are going to be wound. So this is the structure of the stator winding for both induction as well as synchronous. So both of them are going to have very, very similar structure as far as the stator winding structure and the stator structure in general are concerned. And of course, the core is made up of ferromagnetic material. So I will have the core made up of ferromagnetic material. And I am also going to have them basically laminated. So unless it is laminated, I will have huge amount of eddy current losses. So I want to minimize the eddy current losses. So it will be made up of several laminations, which will be stuck together with the help of resins. Of course, they will be insulated from each other with varnish, just like what we did in the case of transformer. Same thing holds good. And as far as the rotor was concerned, we said there are two types of rotor. We talked mainly about the squirrel cage rotor in the last class. Definitely the squirrel cage rotor will also be having the conductors embedded inside the rotor slot. The rotor slot will be in the outer periphery of the rotor, because the rotor will be the internal member. I will have the rotor sitting here. This is the rotor. So if I say the rotor is sitting inside, I'm going to have the rotor essentially having slots in the outer periphery somewhat like this. This is how it is going to be, and the entire thing is completed like this. So all over the outer periphery I will have teeth, and in between the two teeth is the slot basically. And I will have this also laminated. This will also be laminated core, because this will also have induced currents which are alternating in nature. So obviously I can't have them without lamination. So this is also a laminated core, because of which I may have conductors put in each of these slots like this. If it is a cage rotor, squirrel cage rotor, in that case these conductors are going to be thick. So they are actually called as rotor bars. Rather than calling them as rotor conductor, which is thin in nature, these are rotor bars which are really, really thick. So they can be made up of either copper or aluminum. So this may be copper or aluminum. So if it is a low kilowatt motor, it may be aluminum, because we don't care so much about the efficiency. I square R losses may be slightly higher as compared to copper. But if it is a very high capacity motor, the current carried will also be large. So I have to make sure that I square R losses are not too high, and I should not have very low efficiency. Generally large capacity motors we tend to design with a better performance. because every percentage efficiency matters in terms of the energy or the power that is being consumed. So that's the reason generally high capacity machines are paid utmost attention in terms of design. So generally for high capacity motors, it may be copper, right? Whereas for low capacity motors, it may be, aluminum. So if it is tens of kilowatt, we may still call it as low capacity. If you are talking about hundreds of kilowatt, we may call that as high capacity, right? We are not talking about fractional kilowatt at all. Hardly ever three-phase machines are used for fractional kilowatts. So fractional kilowatts, as I told you in yesterday's class, that will be generally only in single-phase case. Most of the times, we use single-phase machines for fractional kilowatt capacity. So what we are going to have in this case is 2 end rings will be there. If I forget about the core, I am going to have essentially the rotor bars being, in the slots, and at the ends they are going to be essentially short circuited with the help of something called end ring. So this is the end ring. End ring will also be made up of aluminum or copper. So they are essentially short circuited. I cannot interfere with the structure of the rotor at all. I can't vary the resistance. I can't vary any of the parameters of the rotor. It is already set in stone. When I designed, I would have designed it with the particular resistivity of the copper material or aluminum material. That's done. I just cannot change it. So this essentially looks like a cage, and that is the reason why it has got the name cage rotor, and it is like the lines on the squirrel's back, so it is generally known as squirrel cage rotor. Yeah. Aluminum has basically higher resistivity. If you compare the resistivity of the two materials, copper will have better current density. Higher current density it will be able to withstand. Aluminum will be able to withstand a lower current density only. And similarly, the resistivity of copper is smaller as compared to aluminum. So if I want a very high capacity motor, I should be looking for which can carry larger current even with a smaller cross sectional area, which is copper. And yet will have lower I square R losses, right? So that will tell on the efficiency. That's the reason, right? So this is going to be end ring. Both these things are called end rings, and these are rotor bars. These are the rotor bars. So this is the typical structure of a squirrel cage rotor, which is really rugged because they are essentially welded together. If I have the rotor conductors which are residing inside the slot, the copper rings will be welded. So you don't have any moving contact anywhere. It will be continuously rotating. Even when it is rotating, you are not having any moving contact. Everything is a solid structure. So you would hardly see much of wear and tear in the case of a squirrel cage rotor. So once you put it in service, you can forget about it for decades on. There is no problem at all. So maintenance-free operation is one of the special selling points, right? Maintenance-free operation is one of the special selling points of the squirrel cage motor, squirrel cage induction motor. So I don't have to maintain it at all, unlike DC machines where I have to play around always with the commutator brush arrangement. Make sure that the spring is holding it tight, touching the commutator and so on and so forth. The other type of rotor which we are yet to discuss, the second type of rotor is wound rotor or slip ring rotor. In the wound rotor, yes. There is no armature. We never call this as armature, by the way. Armature is the specific term used only in synchronous machine and DC machine. Here we don't call it as armature, we only call it as rotor. The rotor, we will not have any control over the rotor current because it is only an induced current. how it gets induced, we are going to see the principle of operation. But the induced current is from the stator side. It is like a transformer action. So if I have no control over the resistance that I can include, or no control over an inductance that I can include in the circuit, whatever is the inherent value of resistance and inductance, that's what limits the current. So there is no way I can play around with the values of current. Whatever is induced EMF, that divided by inherent impedance of the rotor will give me the current. So I don't have any control over the current as far as the rotor is concerned. I can't even measure it. Only if I measure, I can say I want the current to go to this particular value. There is no access whatsoever to the rotor currents as well as the rotor induced EMF. So it's very, very difficult to control the rotor current and the rotor induced EMF as well. Okay? We will look at the operation further, which will probably clarify matters a little better for you. Okay? Fine. As far as the wound rotor is concerned, the structure is very similar to the stator structure. So it is also going to have three-phase windings. That is, the winding structure is similar to the stator winding structure. So I'm going to have three-phase windings basically sitting within your motor's rotor. So if I have basically the rotor structure somewhat like this, I'm going to have maybe A phase at some point, maybe B phase at another point, and C phase at the third point, something like this. I'm going to have A, B and C phase windings basically again spread around the entire periphery, outer periphery of the rotor. So if I have three-phase stator, I have to have a three-phase rotor. If I have wound the stator for 2-pole, 4-pole, 6-pole, 8-pole, whatever configuration, I have to have similar pole configuration for the stator as well as rotor. I can't have different configurations for both. Whereas in cage, all the cage rotor bars will carry any current. We don't know whether it is A phase current, whether it is B phase current, whether it is C phase current. They will happily defect from one phase to another or carry everything together. There is nothing like it is going to be affiliated to a particular phase or particular pole. So they can adjust themselves very nicely to 2-pole, 4-pole, 6-pole, 8-pole, 3-phase, 2-phase, single phase, any configuration. So rotor, when you have squirrel cage rotor, it is absolutely flexible. Absolutely flexible in terms of adjusting itself to any number of phases, any number of poles. So if I have a cage rotor which is working in three-phase induction motor, I can always fix it for a single-phase induction motor as long as it is mechanically feasible and electrically feasible in terms of the current capacity. If the rotor current that is carried by the single-phase machine can be withstood by the three-phase machine as well, I can interchange the rotor, no problem at all. It will completely adjust itself. Whereas wound rotor, it is wound specifically for a particular number of phases and particular number of poles. So I can't interchange a 2-pole machine with 4-pole machine and vice versa. I can't do that. So flexibility is one of the major issues with wound rotor. I will not have flexibility. Not that every other day we are going to change from 2-pole machine to 4-pole machine and interchange the rotors. But if there is a problem, maybe the rotor got defunctional or it has become non-functional, then I can't simply fix up from another machine, I can't put the rotor. That's what I'm trying to say. So if this is the way the conductors are arranged, I can show them if it is star connected. For example, I can show the three-phase conductors somewhat like this. The rotor ones. In a wound rotor, I can show the three-phase windings may be connected in star somewhat like this. Now I have not short-circuited them. Please remember, in squirrel cage it is inherently short-circuited. Here they are not short-circuited. So here slip rings come in handy. I am going to have basically if here is my shaft. Imagine that this is my shaft. Okay? Here is my rotor. Rotor will be generally having a higher diameter. This is my rotor. And the shaft is fixed, or exactly it is going to be engaging clearly with whatever is my rotor structure. So it has engaged with the rotor structure. Now I am going to have one slip ring. That is, it is like a ring which is put on the finger. Similar to that, you are going to have the slip rings sliding over your shaft. But there will be insulation between the slip ring and the shaft itself, because shaft is also made up of iron in all probability. That is also a conductor. So I need to have some kind of insulation between the ring and the shaft itself. So I may have something like a rubber lining or whatever. So that will essentially make sure that the two are insulated from each other. So this is, let us say, for A phase. So maybe this is A phase winding, and I am going to connect this A phase directly to the A phase slip ring, braced or welded. So when the slip rings rotate, the conductors also rotate which are within the rotor. So I will not have intertwining of the slip ring and the conductor. Very similar to what we had in terms of split ring and the armature windings in the case of my DC machine. It is essentially the same. Only thing is, there are no copper mica kind of thing. It's a continuous ring which is made up of copper. So this is going to be one of the copper rings. The second copper ring again will be insulated from the first copper ring. They will be of same thickness, although I have not shown it that way. There should be insulation between these two. And I'm going to have a third slip ring which is corresponding to the third phase. So I will connect basically from, if I may call this as B and this as C. So B will be connected like this, C will be connected like this. So I have three phase conductors being connected to three slip rings. The slip rings rotate, the rotor rotates, the conductor also rotate. So there is no intertwining of the coil when the rotor is rotating. There is no problem. Now we will have brushes which will make contact here. For example, for A phase, I may have the brush here. For B phase, I may have the brush here. And for C phase, I may have one more brush here. So I am going to have three brushes which are stationary. So I basically have, this is my shaft. On that there is slip ring, and the brushes are just touching the slip ring. So as they rotate, the brush is going to be held stationary with the spring arrangement. So we are going to have, please note, a moving contact here. This is moving, right? This is also moving. This is the rotor. And this is also moving because it is housed inside the rotor. The conductors are also moving. I can't short circuit them internally. So what I am doing is, I am trying to bring it out, and then I have put three slip rings, three brushes. From the brush now I can take the connection outside. So these connections will come out and it will rest like armature connections in a DC motor. It will be outside of the machine. So whatever I want to do, I can do. I can short circuit them directly. If I don't want to modify the resistance or inductance, if I want to modify the resistance or inductance, I can include some more resistance, include some more inductance, whatever I want to do. If I want to modify the characteristics, I can measure the voltages, I can measure the currents, because I have brought out all the terminals, so I have complete access to the rotor currents. So slip ring machine clearly has the advantage of having a better control over the rotor parameters as compared to the squirrel cage rotor machine. But squirrel cage rotor machine has the biggest advantage of being rugged. It can't be broken so easily. It is maintenance free. Whereas slip ring rotor, every now and then I have to make sure that the brush arrangement along with the slip ring is working fine, whether they are making proper contact. It goes without saying that there will be sparking. If the contact is not proper, there will be sparking. So very clearly, even slip ring machine is not a good candidate for working in inflammable environment. Because if there is any sparking, it is going to be hazardous. Right? So this has its own advantages, that has their own set of advantages. Let's look at the comparison eventually when we look at the characteristic actually. Right. Now, first of all, why do we have to go for three-phase? Why can't we just work with single phase? Right? Single phase is much simpler. You can just have one winding, that's it. Forget about it. Whereas here I have to have three sets of windings. This is only because when I actually look at a single phase machine, I may have the voltage somewhat like this. Whereas my current, if I assume it's slightly inductive, the current might probably lag behind the voltage by certain angle. Right? And if I try to look at the overall power, right, it is the product of V and I. So this is my voltage, this is my current, this is the case in single phase. Right? So if I look at the power, I'm going to have actually this current will continue like this, right? Because it is alternating in nature. So I'm going to have the power negative during this portion. I'm going to have the power positive during this portion. Again negative during this portion, positive during this portion, and negative during this portion. So this is the product V times I. So the power is not a constant. The power is continuously oscillating, and it is going into the negative direction as well. And what is actually looked upon as the negative power, so that is indirectly contributing to reactive power. So it is going back and forth. The power what flows from the supply into the load or into the motor and then to the load, that is essentially a positive power or real work done. And what is going back and forth in the form of stored field energy, probably in the inductance, and then it is given back during some time. So that is essentially the reactive power. So it doesn't go or contribute towards any useful work. So this is one of the first points as far as the single phase and three phase systems are concerned. In single phase, continuously you are going to have oscillation in the power. You are not going to have a constant power. You are also going to have a good amount of reactive power. That reactive power is essentially not contributing to any useful work done. And also, because I have the power oscillating like this, if I say P is equal to TE times omega, right? Omega is generally governed by mechanical time constant, because the inertia will always make sure that all the oscillations in the torque will not be reflected upon in omega, right? Because the torque oscillations basically are reflecting on the d omega by dt, which is governed by this equation. We have written this several times now. So J d omega by dt indicates that J is going to act like a smoothening factor when I am looking at the variations in the speed with respect to the torque variations, right? So if I say that the speed is fairly constant, especially in a 20 millisecond cycle, I am looking at just 20 milliseconds. During 20 millisecond cycle, I am going to see the speed fairly as a constant, because the mechanical time constants are generally of the order of seconds. Okay? So if that is a constant, very clearly omega is a constant, so T has to essentially reflect the variations in P, right? In power. If the power is oscillating, very clearly from this equation, if omega is a constant, TE has to necessarily reflect the variations in the power. There is no other option. So if the torque is continuously oscillatory, whether I like it or not, there will be very little small changes in omega. D omega by dt will not be 0 at any point in time in a single phase machine. In a single phase machine, as a rule, you will see that the speed will never be a continuous constant. Like if it is 1500 RPM, it may go between 1490 and 1510. It will keep on oscillating. So, if I want a very, very precise control mechanism for the speed, where I cannot tolerate any oscillations in the speed, even small oscillations in the speed, I cannot go for single phase machine. And another thing is, whenever I am going to see there is oscillation in the speed, there will be more vibrations, there will be more noise. So if I am talking about a 1 kilowatt machine, which is a single phase machine, the noise is still tolerable. If I am talking about a 500 kilowatt machine or 850 kilowatt machine like what we use in traction, it will be impossible to withstand that kind of a noise when there is an oscillation. So single phase machines as a rule are not used beyond about 3 to 5 kilowatt. The maximum we use single phase machines is only for 3 to 5 kilowatt, right? Let us now go over to the principle of operation of the three-phase induction machine. For that, we will have to understand something called revolving magnetic field. This is a brilliant discovery made by Tesla. And this essentially states that when you are going to give a three-phase time-shifted current to a three-phase space-distributed winding, you are going to get a revolving magnetic field. Okay? Let us first of all examine really how this is produced. So we are going to look at this graphically first as to why a three-phase time-shifted current given to a three-phase space-shifted winding, why it would produce a revolving magnetic field. So let us try to look at the revolving magnetic field theory. Let us say I am representing the stator with three-phase, not distributed winding because it is difficult for me to draw. So I am going to just draw it with concentrated winding. So let me call this as A and A dash. And I am going to call this as B. And I am going to call this as B dash. And the third one I am going to show C, and this is C dash. These are the three-phase windings, which I am not showing completely, only the ends I am showing, basically in the form of a cross section. Right? Now, A phase axis, if I assume that I am having the dot like this, the A phase magnetic field axis will be this way. So I am just showing the A phase axis somewhat like this, and B axis will be 120 degree shifted, C axis will be 120 degree shifted further. That's it. Right? So I have these three as the magnetic field axis of A, B and C phases respectively. Now, if I am having only one phase winding, first of all let me examine how the magnetic field is going to look like. I am just going to look at only one of the phases at a time. Okay? So let us say I am pumping a A phase current in A phase winding, which is maybe Im cosine omega t, whatever, doesn't matter, at a frequency of 50 hertz. Now if I am actually pumping in this current, so let me call this as Ia with respect to omega t. Right? If I assume that I am pumping in the current through this and then the current is returning through this, whatever, I am going to get the magnetic field in this direction. What do I mean by that? I am going to have probably the north pole here and south pole here and so on. That's it. That's what I am going to get. So in which case, I should say the strength of the magnetic field depends upon what is the strength of the current, because MMF is going to decide how much is the strength of the magnetic field, assuming that the reluctance does not change much. Okay? So in which case, I am going to have essentially maybe a sinusoidal field in such a way that if I say this is theta equal to 0 degree, I am going to get probably the peak located somewhere here, and then it is going to essentially look like this. This is essentially theta. So this is going to be the MMF wave. This is going to be the MMF wave with respect to theta. Please understand, I am drawing the MMF wave with respect to space. What I am drawing as the current is with respect to time. So I am talking about the time. Maybe this is corresponding to, let us say, time t equal to t1. Maybe this is t1. So this is the MMF wave at time t equal to t1. If I say I am looking at time t equal to t2, so I am talking about time t equal to t2. At time t equal to t2, please note, the overall current itself has come down. Right? At time t equal to t2, the current has come down. Because the current has come down, the peak of the MMF wave will also come down in terms of its magnitude. So I am going to get probably this as the MMF wave at time t equal to t2. What I am trying to get at is, if I look at only one phase at a time, I get a standing MMF wave or standing flux wave. That standing wave is pulsating in nature. It's not shifting. It's not traveling. It is standing. So I am going to have basically a standing wave produced whenever I have a single phase excitation. It will not create a traveling or revolving field whatsoever. Right? So what I am looking at when I have the three-phase excitation is, at any point I am going to look at the resultant of all these three phases. If I say this is theta, at an angle theta from A phase axis, I am going to look at what is the resultant of all the three-phase MMFs. That's what I am trying to look at now. Right? So I hope you guys have understood what is a pulsating MMF wave or standing MMF wave, from which we are going to derive basically what is the resultant MMF or resultant field that we are going to get from all the three phases. Right? So if I say what is the MMF of A phase at any point in time, I should say it should be n times Ia, and with respect to theta I am trying to see. So I should write clearly cos of theta, because I am trying to find out the component along theta. Similarly, if I try to look at what is Fb of theta, it will be n is the number of turns in any one of the phases. I am assuming all the three-phase windings are balanced. That means the number of turns are the same in all the three phases. Okay? So I am going to write n Ib times cos of theta minus 120. Right? Because I am looking at basically 120 degrees between these two. So 120 minus theta or theta minus 120. Either way is fine. In the other case, Fc of theta will be n Ic cos of theta plus 120. Now what I have to calculate as the overall MMF will be the summation of all these three MMFs. Before doing this analytically, let me try to look at the whole thing graphically so that you also get a better understanding physically of this. Right? So if I have, let's say, this is my sinusoidal wave as far as A phase is concerned. I am going to draw the other two. So I am just drawing 60-degree intervals, then I am drawing B phase and I am drawing C phase. I'm sorry, I'm not drawing them equally well. They should all be balanced currents, obviously. Okay? So this is IA, this is IB, and this is IC with respect to omega t. Three-phase currents I have pumped into the three-phase distributed winding. Let me look at each of the time instants. For example, let me try to look at the time instant corresponding to t equal to t naught, probably. What is going to be the summation of all the three MMF waves? After all, n is a scalar, so I don't even have to include n. That's fine. I can look at basically what is the summation of IA, IB, IC along with the space, because it's a space distributed winding, right? Let me again read out the directions of what we wrote as A phase is here, B phase is somewhere here, and C phase is somewhere here. This is how we drew the directions, right? So let us try to see what are all the directions at this instant. So at time t equal to t naught, I should say A phase is having only, this is 30 degree approximately. So if it is 30 degrees, I am going to have essentially half of whatever is the peak. I have not drawn it very well, but it is half of the peak because sine 30. Sine 30 is half. So I am going to have basically IA is going to be whatever is the peak, so this will be IM by 2. So this will correspond to FA basically. And if I look at what is the value corresponding to IC, right? IC is also at similar juncture. The zero crossing is here for IC, and this is also about 30 degrees away from the zero crossing. So that will also be IM by 2, and that will be in the positive direction. So I should say my IC is here. So IC is probably here again. This will also be IM by 2, and this is FC. Now this is IB. IB is at its peak, but it is in the negative direction, right? So I'm going to have actually IB similar to this, but in the opposite direction. This is going to be minus B, right? So I have to draw a minus B along this, which will be IM itself. So this will be FB. Right? Now if I add all the three together, right, I will have the resultant by parallelogram law of addition somewhat like this. It is going to be like this. So this is about 30 degrees or 60 degrees. This will be 60, I suppose. This will also be 60. Right? Totally this is 120. Between A and C it is 120. So it is going to be IM by 2 cos 60 plus IM by 2 cos 60 plus IM itself. So it is going to be 1.5 times IM. So I am going to have this to be 1.5 times IM. This is the resultant at time t equal to t naught. If I try to look at another time interval, maybe this zero crossing let me take, this is t equal to t1. So let me try to draw this at t equal to t1. Okay, similar stuff let me try to draw. So at time t equal to t1, I am having IC equal to 0. Very good. So I don't have to draw anything for FC. FC is 0. Right. Now I am going to have IB, which is actually about, from the peak it has moved by about 30 degrees. So 90 plus 30, 120. So it will be equivalent to sine of 120, but in the negative direction. In the negative direction. And if I try to look at what is the value of A at this point, that will also be equivalent to sine of 60. Sine of 60 is root 3 by 2. So I am going to say rather IA will correspond to something like this, which is actually, I am sorry, not this much of length. So it will be root 3 by 2 times IM. This is what is FA. Right? And if I try to draw what is FB, again it is along the negative direction. Please note that this is a negative current. So I'm going to have again FB somewhat like this, which will also be root 3 by 2 times IM. And this is what is FB. Now I have to add these two together. So when I add these two together, I will have it somewhere in the middle, right? This is how it will be. So I'm going to have probably this as the resultant. So the resultant will be root 3 by 2 Im cos of 30. This is 30 degrees clearly. This is also 30 because this is 60. So it will come in the middle. So I'm going to have 30 degrees as the phase shift. So root 3 by 2 Im cos 30 plus root 3 by 2 Im cos 30, which will again become 1.5 Im. You can keep on doing this for every 30 degree interval. You will see that between T0 and T1, the phase shift is 30 degrees. Between this vector and this vector, this was 60 degrees, this has now moved by 30 degrees. That means every time the time shift takes place by 30 degrees in the current wave, there is a 30 degree shift or movement in the MMF wave or the flux wave as far as the space is concerned. So this is space movement, whereas this is time shift. Right? So I should say basically that if I supply 3-phase time distributed current to a 3-phase space distributed winding, I see that I am going to get an MMF wave which will keep on rotating at the same speed as that of the oscillatory speed of the sinusoidal wave, which is the current wave. So I can say if omega is the frequency of the current, then the rotating speed is going to be of the magnetic field. That is going to be omega radians per second in space. Both of them are going to be exactly one and the same. Right? Let us try to see whether we get a similar result even when we are doing it analytically. This is essentially a graphical proof. We are trying to look at the graphical proof as to if we take the component of the MMF wave along a direction theta, are we trying to get ultimately, a revolving magnetic field at all. Please note the revolving magnetic field is having a constant magnitude. That is 1.5 times Im multiplied by the number of turns. Of course, I have neglected that here. That is a scalar multiplication. So what we did in the previous page, we had already written that these are going to be the MMF expressions corresponding to each of the phases, that is A phase, B phase and C phase. And if I want the overall MMF to be calculated, I have to write F total is equal to Fa of theta plus Fb of theta plus Fc of theta. This is what I have to add. And what is Ia? Ia is A phase current, which is also sinusoidally or cosinusoidally oscillating. So I should be able to write Ia equal to Im cos omega t. This I can write as Im cosine omega t. I can write this as Im cosine omega t minus 120 degrees, and this will be Im cosine omega t plus 120 degrees. Right? So let us try to write this n Im cos omega t cos theta. Let me write n commonly, right? Then I'm going to have Im cos omega t minus 120 degrees cos of theta minus 120 degrees plus Im sin omega t plus, cos omega t plus 120 degrees cos theta plus 120 degrees. So let us try to simplify this. You guys are better. Cos A, cos B. So you should say cos of A plus B plus cos of A minus B, or cos of A minus B plus cos of A plus B. Half of that, right? Half of that. Okay. So we are going to have, let's say, f of theta total will be equal to n Im cos of omega t plus theta and cos of omega t minus theta. This is the first one. The second one will be cos of omega t plus theta. There was minus 120 in both. So I should have minus 240. The other one will be cos of omega t minus theta, because minus 120 will get cancelled with minus 120 when I subtract. And the last one will be cos of omega t plus theta plus 240 and cos of omega t minus theta. Of course, the whole thing has to be divided by 2. Right? Half of cos A plus B plus cos A minus B. Omega t minus 120 and theta minus 120. Because we are actually impressing the current which is corresponding to B phase current, which is lagging behind. B phase current is lagging behind. That's how we have shown here also. If you may recall, please note, B phase current is lagging behind the A phase current by 120 degrees. This is lagging behind. Yeah, here space-wise we are showing as though the winding what we have wound for B phase is leading. There is a specific reason. Very good question. Very, very good question. Normally, when we are looking at a synchronous machine, I told you that the winding structures are extremely similar for induction and synchronous machine. Right? If I are looking at a synchronous machine, I have the A phase, B phase and C phase windings. What I had drawn is in such a way that first comes A phase, then comes C phase, then comes B phase. That is the way I have drawn it. But in a synchronous machine, what happens is the stator has the three-phase winding, which is known as the armature of a synchronous machine. The rotor has basically the magnet. The rotor is going to have a north pole and south pole. So what happens is the north pole and south pole of the rotor is being rotated with the help of a turbine. So when it is rotated in anti-clockwise direction, please think about it. First it will meet with A, next it will meet with B, next it will meet with C. So the EMF induced will be such that A phase gets the theta equal to 0 corresponding EMF. The second one gets then after 120 degrees away from the first EMF that is induced in A phase. And C phase gets another MMF or EMF which is corresponding to another 120 degrees away from the B phase. That's why it looks as though this is inverted. Are you getting my point? We always look at the winding with respect to the fact that it is like a generator. For generator operation, if the magnet is being rotated and our conventional direction is anti-clockwise direction of rotation. So when we look at it, We want to always arrange the windings in such a way that A phase comes first, then comes B phase, then comes C phase. Okay. So, you would normally see that it looks as though we have kind of goofed up in the notation, but we have not. Basically, we are looking at the whole thing in generator point of view. That's what it is. Okay. So, if we are looking at it, now, this is the total MMF. Clearly, this plus this plus this is like a three-phase current instantaneous value. If I add IA plus IB plus IC is always 0. So, this component is going to vanish. This will not give me any resultant value because it is like IA plus IB plus IC, where IA is cos of theta or cos omega t, IB is cos omega t minus 120, or I can write it as plus 240. Similarly, I can write it as cos omega t plus 120 for IC, which will be equivalent to cos omega t minus 240. So, clearly this is like a normal three-phase system where the instantaneous values add up to 0. Right? So, this will not contribute to anything, whereas this is going to contribute to 3NIM by 2 multiplied by cos of omega t minus theta. So this particular expression actually tells me that what I get as the MMF wave or the flux wave in the air gap, that is, if I look at the stator which is having the winding along its inner periphery like this, I am going to have basically the magnetic field produced here. This is where the magnetic field is going to be produced in the air gap, in the inner surface of the stator. So, that is going to be a cosinusoidal wave probably, or a sinusoidal wave, where the peak is continuously getting shifted. So, I will have continuously the peak probably lying here, lying here, lying here, lying here, and so on, where I am going to have omega t equal to theta at any point in time, that is omega t minus theta equal to 0. That corresponds to the point at which the peak is located. Right? So, I am going to have basically, it is as though I am going to have a north pole and south pole, and I rotate it physically at the same speed as that of omega. Right? I am not having really physically any magnet here. What I have done is only to have a three-phase time distributed current, I have given that to a space distributed winding. That has created the effect of actually having a magnet physically and rotating it at a speed which is known as synchronous speed. We call this speed omega as the synchronous speed. So, the synchronous speed is fully determined by the frequency of the current that I am injecting to my three-phase machine. And it has to be a balanced current. So, that's why I say that this is a fantastic discovery by Tesla. And as far as I remember, there is hardly any design difference between what Tesla designed in 1879 or 1880 and today's induction machines. Very, very limited difference in the design. So, three-phase became extremely popular only after this particular discovery was made, and Tesla made the first induction machine, which actually became the workhorse of all the industry.